So I have distributed a review sheet for the first exam. First exam is in person on campus on Wednesday. Let me just write that down to make sure everybody sees it. Exam 1, in person on campus Wednesday, which is October 19, from 9 o'clock to 10:40 a.m. Covering chapters 1, 2, and the first 2 sections of chapter 5. So I'm happy to review any material that you like, or to discuss some material that I didn't talk about when we met on campus last week. Any questions from the review sheet you would like me to do? Well, okay. So if not, let me begin to discuss a little bit or review a little bit from chapter 5, which is second order equations, and then in particular, second order equations with constant coefficients. So the fundamental theorem on this subject, which is not extremely complicated to prove, but certainly goes beyond the prerequisites in mathematics for this course, is theorem 5.1.1. And we use this all the time, whether you realize it consciously or not. So we have functions P and Q, which are continuous on an open interval from A to B. And we let x naught be any point in this open interval. So on the number line, here's A, here's B. We're looking at this open interval, and we choose any point x naught in that open interval, and we let k naught and k1 be arbitrary real numbers. So we consider the initial value problem, IVP, the initial value problem, which is to solve the differential equation y double prime plus p of xy plus q of x equals 0. This is a homogeneous initial value problem. So this is a second order equation because it involves the second derivative of y. It's linear because, oops, this should be y prime and y. It's linear because you have y, the first derivative, and the second derivative of y occurring sort of as individual terms, multiplied maybe by powers of x, or functions of x, p and q, but there's no power of a derivative or a product of like y times y prime. The y prime, and y double prime stand alone. So this differential equation is a linear second order homogeneous equation, and we want to find the solution which satisfies the initial condition that y at x naught is equal to the number k naught, and y prime of x naught is equal to the number k1. So here's the differential equation. We want to find a solution that satisfies this initial condition. It's a second order equation, and there are 2 initial conditions, one for y and one for y prime. And the theorem says the initial value problem always has a unique solution on AB. That means so long as P and Q are continuous on the open interval from A to B, if you take any point x naught in the interval and any numbers k naught and k1, the initial value problem, first of all, has a solution. A solution exists, and it has only one solution. The solution is unique. So this is the fundamental theorem that we're using. We'll extend it next week to inhomogeneous equations where the right-hand side isn't zero, but some other function. But in the homogeneous case, which is always the simplest case, such an equation always has a solution. And these functions P and Q don't have to be constant. They're simply continuous, right? So any continuous function. And so that's the fundamental theorem. The second very important concept is that of having a fundamental system of solutions. So actually, maybe I should start off with just what is one of the most important examples. So here's an example. So we take a number omega, which is positive, and we would consider the equation y double prime plus omega squared y equals 0. And so this is linear second order homogeneous. What are the functions P and Q in this case? If you think of this as y double prime plus 0 times y prime plus omega squared times y equals 0, the coefficient of y prime is just the function which is identically 0. The coefficient of y is the function q of x, which is the constant function omega squared. So these are certainly constant. And one solution of this equation is y1 equal to the cosine of omega x. Because if you differentiate this once, y1 prime, you get minus omega sine omega x. And if you differentiate this a second time, you get another factor of omega, you get minus omega squared cosine omega x. And if you take omega 1, if you take y1, multiply it by omega squared, what do you get? So y double prime, y1 double prime, plus y1 plus omega squared y1, that's minus omega squared cosine omega x, that's y1 double prime, plus omega squared y1 cosine omega x. Well, these cancel. This is 0. So this is one solution of this equation. And if we take y2 to be the function sine of omega x, we differentiate this once, we get omega cosine omega x. We differentiate this a second time, we get minus omega squared cosine omega x. So y2 double prime plus omega squared y2, that's minus omega, this is sine. We get minus omega squared sine omega x plus omega squared y2 sine omega x. Again, minus plus, we get 0. So these are two solutions of this differential equation. Right? And it follows that if we take any linear combination of these, we take y to be any constant c1 times cosine omega x plus c2 times sine omega x, this is also a solution. For all c1 and c2. So In fact, it turns out this is the general solution, but we haven't proved that yet. That is, it turns out that every solution of this differential equation is this kind of linear combination of cosine omega x and sine omega x. Right? By the way, our functions p and q are continuous on the whole real line, that is the open interval from minus infinity to plus infinity. So the open interval AB in this case is the interval from minus infinity to plus infinity. And of course, this makes perfect sense for any x from minus infinity to plus infinity. Now, suppose we actually had a initial value problem. We wanted to find the solution of our differential equation, right? Differential equation y double prime plus omega squared y equals 0, but satisfying the initial condition that y of 0 equals 1 and y prime of 0 equals, I don't know, let me just change the number, say y of 0 equals 2 and y prime of 0 equals minus 1. So that means we have to find C1 and C2 that satisfy, so that y satisfies this initial condition, right? For any C1 and C2, this is a solution of the differential equation. The question is there a choice of C1 and C2 which satisfies these initial conditions? So y of 0, if you plug in x equals 0, you get C1 plus 0. Because cosine of 0 is 1, sine of 0 is 0. So C1 plus 0 has to equal 2. So C1 equals 2. That's easy. And what is y prime of 0? When you differentiate the cosine, you get the sine. Sine of 0 is 0. When you differentiate the sine, you get the cosine. Cosine of 0 is 1. You get 0 plus C2. That has to equal minus 1. So C2 is minus 1. So the unique solution of the differential equation that satisfies our initial condition is y equals 2 cosine omega x minus sine of omega x. This has the value 2 when x is equal, oops, sorry, I made a mistake. When I differentiate this, it's always good to do things right. When I differentiate the sine, I get omega times the cosine. So there's an omega here. So omega C2 is minus 1. So C2 is minus 1 over omega. So this is minus 1 over omega, sine of omega x. And if you plug x equals 0, you get 2. If you differentiate with respect to x, here you get minus cosine of omega x. When x is 0, that gives you minus 1. Okay. So this is one of the, so this is a basic problem on second order equations. Is there any question about this? I mean, this is, in terms of doing the mathematics, about as easy as it will get on the exam. Okay, now, when we're trying to solve these second order equations, there is the notion of a fundamental system of solutions. So suppose we have our homogeneous linear equation, y double prime plus p of x y prime plus q of x y equals 0. Where p of x and q of x are continuous functions on this open interval from a to b. We say that a set of solutions, two solutions, y1, y2, is a fundamental set, is a fundamental set of solutions of this differential equation. Call this equation star. It's a fundamental set of solutions of that differential equation if every solution is a linear combination of y1 and y2. A linear combination of two functions means some constant c1 times y1 plus a constant c2 times y2. So we didn't prove this, but for example, we didn't prove it yet. For the differential equation y double prime plus omega squared y equals 0, where omega is positive, a fundamental set of solutions is y1 equal to cosine omega x and y2 equals sine omega x. Now, this is a fundamental set of solutions. We saw that each of these functions is a solution. Because this equation is linear, every linear combination of these two functions is a solution. And it turns out that every solution is a linear combination of these. Now, there's one other term that we introduce here, which is a pair of functions. So functions y1 and y2 are linearly dependent if y2 is some constant multiple of y1 for some c. And these functions are linearly independent if y2 is not a constant multiple of y1. Or an equivalent way of saying that is if y2 over y1 is not a constant. So for example, cosine omega x and sine omega x are linearly independent because if I take the ratio cosine omega x over sine omega x, that's the cotangent of omega x, and that's not constant, right? If you graph the cotangent, it oscillates. So cosine omega x and sine omega x are linearly independent. If you take functions like e to the 2x and e to the 3x, these are linearly independent. Why? Well, if you take the ratio, say e to the 2x over e to the 3x, that's e to the minus x, that function looks like that. It's not a constant. And in fact, if you take any two numbers, a different from b, then e to the ax and e to the bx are independent because the ratio e to the ax over e to the bx, which is e to the a minus bx, isn't constant, right? If a is different from b, if a is bigger than b, you have a exponentially increasing curve, and if a is less than b, you have an exponentially decreasing curve, but it's not constant. So different exponential functions, any two distinct exponential functions are linearly independent of each other. Okay. And there's an important criterion, it's actually a very simple test, to tell when two functions are linearly independent. So this is a kind of theorem which is proved. So if you have two functions, what is called the Wronskian of two functions, w of y1 and y2. This is the function y1, y2 prime minus y1 prime, y2. You could write this as a determinant. This is like the determinant of the matrix y1, y2, y1 prime, y2 prime. But this is called the Wronskian. And if y1 and y2 are solutions of my differential equation, differential equation doesn't change. It's y double prime plus p of x y prime plus q of x y equals 0. If y1 and y2 are solutions of my equation, then y1 and y2 are linearly independent if and only if, that's what this double-headed arrow means, if and only if and only if y1 and y2 are linearly independent, if and only if, what happens? The Wronskian of y1 and y2 is not 0. Now, the Wronskian is a function of x. It just has to be non-zero for some x naught in the open interval from a to b, where we're looking for solutions of the differential equation. It's actually a very interesting exercise to prove this is true. And let's see. How can we show something about this? So let's start with the preliminary result. So in the text, this is theorem 5.1.4. So again, we have our differential equation, y double prime plus p of x y prime plus q of x y equals 0. And so this is our differential equation, and y1 and y2 are solutions. So recall that the Wronskian of y1 and y2 is the function y1, y2 prime minus y1 prime, y2. And the theorem says that for any x naught in the interval from a to b, that's an interval where the functions p of x and q of x are continuous. The Wronskian, as a function of x, is the value of the Wronskian in x naught times e to the minus the integral from x naught to x of p of t dt. So this Wronskian, you see, actually, the formula only depends on p. It doesn't depend on q. And what else can you say about this? This is an exponential. An exponential is always greater than 0, right? The graph of the exponential function is always positive. Could be increasing or decreasing, but it's always positive. So if w of x naught is positive, the Wronskian is always positive. If w of x, this means if w of x naught is negative at some point, this is always negative. And if there's one point at which w of x naught is 0, then the Wronskian is identically 0. So this is a very useful formula. It's called Abel's formula, after a great Norwegian mathematician named Niels Henrik Abel, Abel's formula. Okay. So how can we prove this? Well, we can prove this by solving a first order differential equation. So proof. So we have W is equal to y1, y2 prime minus y1 prime, y2. So if we differentiate the Wronskian, we get y1, y2 double prime plus y prime, y1 prime, y2 prime. That by the product rule is the derivative of the first term, minus the derivative of this, y1 double prime, y2 minus y1 prime, y2 prime. And you see these terms cancel. So we get y1, y2 double prime minus y1 double prime, y2. But y1 and y2 are solutions of this differential equation. The differential equation says, this is the differential equation. If I just bring the second derivative on one side and put everything else on the other, this says that y double prime is equal to minus p of x y prime minus q of x y for any solution. And y1 and y2 are solutions. So this is y1 and y2 double prime will be minus p of x y2 prime minus q of x y2 minus y1 double prime, which by this will be minus p of x y1 prime minus q of x y1 times y2. So let's see what we get and hope there's some cancellation here. I have minus p of x y1 y2 prime minus q of x y1 y2 plus, minus is plus, p of x y1 prime y2 minus times plus q of x y1 y2. And it looks like these two terms cancel, and I'm left with these two terms. These two terms, if I factor out a minus p of x, I get minus p of x times y1 y2 prime minus y1 prime y2. But this is exactly the Wronskian. This is minus p of x times w. Right. So again, this is exactly the calculation which is done in the book on page 200. So, you're supposed to be reading the book and you can go through and see this in more legible detail if you like. But what this says is the Wronskian w is a function of x, and it satisfies this condition, which is a first order condition. That is, the Wronskian is equal to minus p of x times w. Right? And this is a first order linear differential equation, which is separable, right? It says y prime over w is minus p of x. So if you integrate both sides with respect to x, you get, this is the log of w is minus the integral, let's say from x naught to x of p of t dt, plus maybe a constant. So if you exponentiate, you get w of x is e to this constant, e to the minus the integral of x naught to x p of t dt. And if you evaluate this at x naught, and w of x is either always positive or always negative. So you can choose this constant that means make this a c. So w of x is c e to the minus integral of x naught to x p of t dt. If you evaluate this at x equal to x naught, w of x naught is c e to the minus the integral from x naught to x naught of p of t dt. An integral from a point to itself is 0. So this is e to the 0 or 1. So this is c. So my constant is w of x naught. So this proves Abel's formula. W is equal, w of x is w of x naught times e to the integral from minus x naught to x p of t dt. So this says that either the Wronskian is identically 0 or it has no zeros on the interval from a to b. It's either always positive or always negative. So let's just compute the Wronskian of some pairs of functions. Let's go back to the differential equation y double prime plus omega squared y equals 0. So we have one solution, cosine omega x, and another solution, sine omega x. So y1 prime is minus omega sine omega x. Y2 prime is omega cosine omega x. So if we compute the Wronskian directly, it's the determinant of the matrix cosine omega x sine omega x minus omega sine omega x omega cosine omega x. So that's this omega times cosine squared omega x minus, there should be an omega there, minus this times this. So it's minus omega sine squared omega x. Minus times minus is plus. This is omega cosine squared omega x plus sine squared omega x. And this is 1, so this is just equal to omega. And we took omega positive, so this is not equal to 0. So this is a direct calculation of the Wronskian. And suppose we use Abel's formula. Abel's formula says the Wronskian is the Wronskian at some point times e to the minus integral x naught to x p of t dt. But p of t is 0. Right? It's the coefficient of y prime. So this is e to the 0, which is 1. So this is w of x naught. So Abel's formula tells us that the Wronskian is constant, though it doesn't give us the exact value. The exact value is omega. Let's look at one more example.
Professor,
Yes, sir.
before that, the problems at 1 today, you said we can make more by appointment. Would it be possible to meet with you tomorrow as well at around 12?
It should be possible.
Okay.
I don't see. Yeah, it should be possible, but send me an email to remind me, And then I'll set that up as another problem session time.
Thank you. I'll send you an email now.
Okay, very good. So suppose we have this differential equation, x squared y double prime plus xy prime minus 4y equals 0. Now, this is not in the form we like. The form we like is y double prime plus p of x y prime plus q of x y, where the coefficient of y double prime is 1. And here the coefficient is x squared. So before we try to proceed, we want to put this differential equation in this form, and we can do that by dividing through by x squared. But you can't divide by 0. So this equation for x different from 0, if you divide, then you can divide by x squared. You get y double prime plus x over x squared y prime minus 4 over x times y, or this is the same as y double prime, x over x squared is 1 over x, y minus, minus 4, dividing by x squared, minus 4 over x squared, y equals 0. So now my p of x is 1 over x, and my q of x is minus 4 over x squared. And this has to be, these have to be continuous on some open interval. The open interval can't contain 0, so we actually have two choices, which means in effect we have two different problems to solve. So these are continuous on the open interval from 0 to plus infinity, and on the open interval from minus infinity to 0. Open means you don't include the endpoint, so 0 is not included. So we have two different intervals on which to try to solve this differential equation. Now, it turns out that one solution of this equation is y1 equals x squared, and another solution is y2 equals 1 over x squared. So let's check. If y1 is x squared, y1 prime is 2x, and y1 double prime is 2. In that case, y double prime plus 1 over x times y1 double prime plus 1 over x y1 minus 4 over x squared y1 prime minus 4 over x squared y is equal to y1 double prime is 2 plus 1 over x y1 prime, which is 2x, minus 4 over x squared times y1, which is x squared. This is 2 plus 2 minus 4 is 0. So this checks. If y2 is 1 over x squared, which is x to the minus 2, y2 prime is minus 2x to the minus 3, and y2 double prime is minus 2 times minus 3 is 6x to the minus 4. So if we calculate y2 double prime plus 1 over x y2 prime minus 4 over x squared y2, y2 double prime is 6 over x to the 4th, plus 1 over x y2 prime, which is minus 2 over x cubed, minus 4 over x squared times y2, which is 1 over x squared. So we get 6 over x to the 4th minus 2 over x to the 4th minus 4 over x to the 4th, which is 0. So that checks. So each of these functions is a solution of the differential equation. So let's compute the Wronskian in two ways. So again, the differential equation was y double prime plus 1 over x y prime minus 4 over x squared y equals 0. And we had one solution was equal to y1 equals x squared, and y2 is 1 over x squared. So y1 prime is 2x, y2 prime is minus 2 over x cubed. So the Wronskian is the determinant of x squared 1 over x squared, 2x minus 2 over x cubed. When you take the determinant, it's this times this, x squared times minus 2 over x cubed, minus this times this, 1 over x squared times 2x. This is equal to minus 2 over x, minus 2 over x. So I get minus 4 over x. So from the definition, that is the Wronskian. What about by Abel's formula? So the coefficient of y prime is 1 over x. So if we take, so p of t, p of x is 1 over x, p of t is 1 over t. The integral from x naught to x, p of t dt, is the integral from x naught to x of 1 over t dt. That's the log of x over x naught. And so w of x is w of x naught for any point x naught, not 0, times e to this, log of x over x naught. And e to the log of something is just the something. So this is w of x naught times x naught over x. And the Wronskian is minus 4 over x naught. So this is minus 4 over x naught times x naught over x, which is minus 4 over x. This is, we're taking the value of the Wronskian at some point from this formula. And we get exactly what we're supposed to get. So what is the Wronskian's connection to our original problem? The original problem is, how do you know if two solutions of a differential equation form a fundamental set of solutions? And how do you know if a pair of solutions are linearly independent? So in the text, this is theorem 5.1.5, which says for our differential equation, with solutions y1, y2, these are solutions on the open interval from A to B. Y1 and Y2, these two solutions are linearly independent, if and only if the Wronskian of y1 and y2 is different from 0 for all x. So there's a connection between being linearly independent and having a Wronskian, which is a non-zero function. We already saw that the Wronskian is either identically 0 or it's never 0. Okay. So let's show, so let's call this W of X, but it's the Wronskian. So suppose the Wronskian is equal to 0 for some x naught in AB. So here we have this open interval from A to B, and there's a number x naught in that interval where the Wronskian is 0, which means the Wronskian, of course, is identically equal to 0. Now, let's look at the function y1. If y1 is always equal to 0, then y1 and y2 are linearly dependent. I want to show that if the Wronskian is ever equal to 0, we want to show y1 and y2 are linearly dependent. That is, one is a scalar multiple of the other. If y1 is always 0, then y2 is a scalar multiple. Let's see, how do I want to say this? Yeah, if y1 is always equal to 0, identity equal to 0, then y1 is 0 times y2. y1 is a scalar multiple of y2, so these are dependent. So we can assume y1 is not equal to 0 for all x. So there's some interval. The function y1 is continuous. If it's positive somewhere, it's positive on some whole interval I. And if it's negative somewhere, it's negative on sub-interval I of this interval from A to B. So if y1 is not equal to 0, then y1 is different from 0 on some sub-interval I from A to B. So this is something that to understand, and again, I'm following the text very closely here because the arguments are a little bit subtle. This is something you have to think about. It's not instantaneously obvious. So y1 is not 0 on this subinterval. So y2 over y1 is defined on this subinterval I. And it's a quotient of differentiable functions, so you can differentiate it. If you take y2 over y1 prime by the quotient rule, this is y1 squared in the denominator, the derivative of the numerator times the denominator minus the denominator times the derivative of the numerator. And if you look at this, this numerator is exactly the Wronskian over W1 squared. And the Wronskian is 0 everywhere. If it's 0 at one point, it's 0 everywhere. So this is 0, which means y2 over y1 is a constant. If a derivative of a function is 0, the function is a constant. So y2 is equal to a constant times y1. So that means that at least on this subinterval I, y2 is a scalar multiple of y1. But y2 minus cy1, this is a linear combination of two solutions of the differential equation, is a solution of the ordinary differential equation. And it's identically 0 on a subinterval. That means it's identically 0 everywhere. So if the Wronskian is 0 at a single point, then your pair of functions is linearly dependent. But suppose the Wronskian is non-zero everywhere. So again, we have y double prime plus p of x y prime plus q of x y equals 0. And the Wronskian of our two solutions, y1 and y2, are solutions. The Wronskian is not equal to 0 for all x in the interval from a to b. So y1, remember the Wronskian is equal to y1, y2 prime minus y1 prime, y2. If this is different from 0, that means y of x is not equal to 0 for all x. Otherwise, this would be identically equal to 0. And we're assuming the Wronskian is not 0 in this case. So if the Wronskian is non-zero, and what do we know? Well, we just did a calculation. We just calculated y2 over y1 prime is equal to w over y1 squared. And on a subinterval where y1 is not 0 and the Wronskian is non-zero, this is not equal to 0. So y2 is not a constant times y1. And they're linearly independent. So this in the text, this is theorem 5.1.5. And if you're interested in really understanding mathematics, differential equations, or if you like calculus, it really is worthwhile going through this proof in the text very, very carefully and trying to understand the mathematical arguments. And when you put everything we've just talked about together, we get theorem 5.1.6, which is really a kind of a summary. So we always are in this situation. We have a linear differential equation, second order and homogeneous. P of x and Q of x are continuous functions on an open interval from a to b. And y1 and y2 are solutions. So y1, y2 are a fundamental set of solutions of the differential equation, which is the same as saying that the general solution, every solution, is a linear combination of C1, Y1 plus C2, Y2. And if and only if Y1 and Y2 are linearly independent functions, if and only if the Wronskian of Y1, Y2 is different from 0 at some point in the interval from A to B, if and only if the Wronskian is non-zero for all points X in AB. So Abel's formula shows that the Wronskian is non-zero at some point, if and only if it's non-zero at every point. We prove that a pair of solutions is linearly independent if and only if the Wronskian is non-zero. So that proves these three statements. This is the definition of fundamental set of solutions. And how do we show again that we have a pair of functions is linearly independent if and only if they give you the general solution? Let's see. Maybe that's the one little bit that I haven't proved yet. So let me do that. So suppose Y1 and Y2 are solutions. So again, here we have our differential equation. And we want to solve this equation with the initial condition that y of some point x naught is equal to k naught and y prime of x naught is some k1. So here we have this initial value problem. So under what conditions y1, y2 is a fundamental set if and only if you can find some linear combination C1, Y1 plus C2, Y2 at X naught is equal to K naught. And when you differentiate C1, Y naught prime, Y1 prime of X naught plus C2, Y2 prime of X naught equals K1. So you have a fundamental set of solutions if and only if for all X naught in the interval from A to B, and for all numbers K1 and K2, you can solve these equations. There exists C1 and C2 that satisfy these two equations. This is two linear equations and two unknowns. So you've reduced this to high school algebra. And if you solve for C1 and C2, that is, if you eliminate like C2, if you multiply this equation by Y2 prime and this equation by Y2, you eliminate the C2. And what you'll get is that well, you'll get C1 times Y1 of X naught, Y2 prime of X naught minus y prime of x naught, y2 of x naught equals, let's say I multiplied this equation by y2 prime equals k naught, y2 prime of x naught minus k1, y2 of x naught. I have to find a C1 that solves this equation. This is the Wronskian. This is C1 times the Wronskian x naught equals this right-hand side. And you can solve this equation if the Wronskian is not zero, you just divide by it. But if the Wronskian is zero, for some choices of k naught and k1, this isn't going to be zero. You can't solve this equation. So you have a fundamental set of solutions if and only if the Wronskian is non-zero, which is the same as the functions being linearly independent. And that is the whole theory of homogeneous linear second order equations. So that's all a lot to think about, but we're moving not too fast through the syllabus, and it's just a little bit more about second order equations. Let's just review about the constant coefficient case. So the equation is ay double prime plus by prime plus cy equals 0. And we look for solutions of the form e to the rx. And e to the rx will be a solution if and only if r solves the quadratic equation ar squared plus br plus c equals 0. So r is minus b plus or minus square root b squared minus 4ac over 2a. So in the first case, b squared minus 4ac is a positive number. So what's under the square root is positive, and we have two non-zero square roots. So let's see if there was any sort of, right? In any case, there are two roots. So say you could have R1 is minus b plus the square root of b squared minus 4ac over 2a. And R2 was minus b minus the square root of b squared minus 4ac over 2a. So one solution would be y1 equals e to the r1x. Another solution would be y2 equals e to the r2x. If you actually calculate r1 minus r2, the difference of these two numbers, the b parts cancel, and you get the square root of b squared minus 4ac over a. Right? Subtract r2 from r1, you get this, which is different from 0. So if I take y1 over y2, that's e to the r1x over e to the r2x. That's e to the r1 minus r2x. That's a non-zero function. This exponent is non-zero. This is different from 0. Sorry, it's not even equal to a constant. It's a function. So y1, y2 are linearly independent functions. Therefore, they form a fundamental set of solutions of the differential equation. So in this case, which is the simplest case, when the associated quadratic equation has two real roots, distinct real roots, you get a fundamental set of solutions. The second case which is interesting, is when b squared minus 4ac equals 0. So r is minus b over 2a. There's only one r. So e to the rx is one solution. And we showed that y2 equal x e to the rx is a second solution. And again, y1 over y2 is 1 over x, which is not 0. So these are linearly independent and therefore a fundamental set of solutions. So this is case 2. In case 3 is b squared minus 4ac is negative. So you have r is minus b plus or minus the square root of b squared minus 4ac over 2a. If b squared minus 4ac is negative, I can write this as minus omega squared, where omega is some positive number. So I have r is equal to minus b over 2a plus or minus the square root of minus omega squared over 2a, which is minus b over 2a plus or minus omega over 2a e to the minus 1i. It's this complex number. And in this case, we have two solutions. Again, y1 and y2. y1 is going to be e to the minus b over 2a, the real part of this, times the cosine of something, and y2 will be e to the minus b over 2a times the sine of something. And the something is this omega over 2a. So with these formulas, you can solve all constant coefficient equations. Right? Let me do just one or two examples. And I just make up numbers at random that say y double prime plus 2y prime plus 3y equals 0. How do we solve this equation? So we have the quadratic equation r squared plus 2r plus 3 equals 0. So r is minus 2 plus or minus the square root of b squared minus 4ac over 2a. This is minus 2 plus or minus the square root of minus 8 over 2, which is minus 1. See, square root of 8 is 2 root 2 plus or minus root 2i. Right. B squared is 4. 4ac is 12. 4 minus 12 is 8. Square root of 8 is 2 root 2. 2 root 2 over 2 is root 2. Minus 2 over 2 is minus 1. That's my quadratic equation. So what are my solutions? y1 is equal to minus 1 e to the minus 1 times x times the cosine of root 2x, and y2 is e to the minus x, the sine of root 2x. So let me just check. Let me just check y1. If this is y1, y1 prime is minus e to the minus x cosine root 2x plus e to the minus x times the derivative of cosine root 2x, which is minus root 2 sine of root 2x. And if I differentiate this again, I get e to the minus x cosine root 2x minus e to the minus x. Again, the derivative of cosine root 2x is minus, makes this a plus, root 2 sine root 2x. minus the derivative of this, e to the minus x has derivative minus e to the minus x, makes this plus root 2 e to the minus x sine root 2x, minus root 2 e to the minus x. Derivative of sine root 2 is root 2 cosine root 2x, and root 2 times root 2 is 2. So y1 double prime is e to the minus x minus 2e to the minus x. That's minus e to the minus x cosine root 2x, and root 2 plus root 2 plus 2 root 2 e to the minus x sine root 2x. So if I take y1 double prime plus 2y1 prime plus 3y1, that's equal to this, minus e to the minus x cosine root 2x plus 2 root 2 e to the minus x sine root 2x plus 2 times y prime. So 2 times this is minus 2 e to the minus x cosine root 2x minus 2 root 2 e to the minus x sine root 2x plus 3y1. y1 was plus 3 e to the minus x cosine root 2x. And we see these two terms cancel. Minus 1 minus 2 is minus 3 plus 3 is 0. So those cancel and we get 0. So that checks. Okay, that's the story. So that's a kind of review and trying to generate some understanding of like the mathematical principles involved. And that's where we are. Any questions before we quit for the morning? Okay, then we're done. Again, in person on campus, Wednesday morning, 9 o'clock. I won't be there. Someone will be proctoring the exam for me, but I will be available on Zoom throughout the entire exam. If you have a question that the proctor needs to transmit to me. Okay. All right. Be well, everyone.